What does it mean when a volcano does not erupt, yet the land above it continues to rise, fracture, shake, and shift? And what should scientists make of a magnitude 4.7 earthquake that struck only a few kilometers beneath the surface, followed by more than 1,000 smaller earthquakes in less than 2 days? At Campi Flegrei, these are no longer theoretical questions. New data released by Italy's National Institute of Geophysics and Volcanology, or INGV, now provide an unusually detailed picture of what happened during the seismic swarm that began on July 31st, revealing changes in the way the central caldera moved and fractured. The earthquake itself was extraordinary by Campi Flegrei standards. At 7:46 in the evening local time on July 31st, a magnitude 4.7 earthquake struck beneath the Solfatara area at a depth of approximately 2.4 kilometers, or about 1.5 miles. INGV says it was the most strongest earthquake recorded at Campi Flegrei since instrumental seismic monitoring began in the early 1970s. Its moment magnitude was estimated at 4.4, an important distinction because different magnitude scales measure different properties of an earthquake. The event then opened the door to a rapidly unfolding swarm beneath the central caldera. Within less than 2 days, the seismic sequence produced a remarkably dense cluster of earthquakes. Routine monitoring initially identified more than 400 events, but researchers subsequently applied an artificial intelligence system to the complete waveform archive. That analysis detected and located more than 1,000 earthquakes between July 31st and August 2nd, more than twice the number identified during the preliminary review. The difference matters because tiny earthquakes can reveal structures and movements that disappear inside ordinary seismic noise. Instead of seeing only the largest shocks, scientists were suddenly able to examine a much finer map of how the caldera responded. The new picture is important because Campi Flegrei is not behaving like a conventional earthquake zone. It is a vast volcanic caldera whose present structure was shaped by enormous eruptions and collapses, including the Campanian ignimbrite roughly 40,000 years ago and the Neapolitan yellow tuff roughly 15,000 years ago. The caldera spans approximately 15 kilometers, or about 9 miles across, and its modern landscape contains towns, roads, ports, and densely populated urban areas. The seismicity therefore unfolds inside a complicated geological system where magma, hot fluids, fractured rock, and tectonic stresses interact beneath a heavily inhabited landscape. That interaction is at the heart of bradyseism, the unusual phenomenon for which Campi Flegrei has become internationally known. Bradyseism describes the repeated rising and falling of the ground over long periods. During uplift phases, seismicity commonly increases as the crust is deformed and existing faults are stressed. INGV reports that the central part of Campi Flegrei has risen by more than 4 meters, or roughly 13 feet, since 1950, when all the alternating uplift and subsidence episodes are considered. The current unrest is therefore part of a much longer cycle, rather than an isolated sequence created by one earthquake. Yet the latest data add an important detail to that picture. The July 31st earthquake did not simply shake the caldera and disappear. INGV reports that several GNSS stations in the central caldera recorded discontinuities in their time series during the earthquake and subsequent swarm. Tiltmeters and dilatometers also recorded offsets associated with the more energetic events. In geophysical monitoring, such offsets can represent abrupt changes in the measured position or deformation of the ground. They are therefore significant because they show that the earthquake sequence was accompanied by measurable deformation, rather than being purely a matter of vibrations passing through otherwise stationary ground. That distinction deserves careful attention, because dramatic descriptions of permanent displacement can easily outrun what the measurements actually demonstrate. The newly released INGV material confirms measurable discontinuities and offsets in deformation monitoring records, but it does not provide evidence that the entire central caldera suddenly dropped or shifted by a single enormous distance, nor does it establish that magma broke through toward the surface. The more defensible conclusion is more subtle. The earthquake and swarm produced measurable deformation signals superimposed on an already ongoing bradyseismic process. Scientists now have to determine precisely which part of that deformation was co-seismic and which part belongs to the continuing longer-term unrest. The geometry of the earthquake sequence makes that question even more interesting. The magnitude 4.7 event began beneath Solfatara at approximately 2.4 kilometers or 1.5 miles depth. Afterward, seismicity migrated generally toward the southwest and became, on average, shallower. Many of the later earthquakes occurred between roughly 1 and 2 kilometers, or about 0.6 to 1.2 miles below the surface. The sequence eventually extended toward the Monte Olibano lava dome, where earthquakes were generally less than 1 kilometer, or about 3,300 feet, deep. The swarm therefore traced a changing pattern through the shallow central caldera. That shallowness is one reason the July event was felt so strongly. Earthquakes occurring only a few kilometers below the surface can deliver intense shaking to the area directly above them because seismic energy has less rock through which to dissipate before reaching buildings and infrastructure. INGV notes that all of the earthquakes analyzed in this swarm were located within the upper 3 kilometers, or approximately 1.9 miles, of the crust. The combination of shallow hypocenters and a densely populated urban environment helps explain why a magnitude 4.7 earthquake can have consequences that appear disproportionate when compared with larger earthquakes occurring much deeper underground. The strongest evidence about the faulting mechanism also points toward a system under extension. Analysis of the seismic waveforms indicates that the magnitude 4.7 earthquake had a predominantly extensional focal mechanism, meaning the rocks were being pulled apart across the fault system. The preferred fault orientation was generally northeast to southwest, with a steep dip estimated at approximately 40 to 60 degrees. There was also a component of lateral or strike-slip movement. That combination matters because it reveals that the earthquake was not simply a straightforward vertical collapse. Instead, several types of deformation were occurring together within the fractured volcanic crust. The magnitude 3.8 earthquake that followed at approximately 8 in the evening also displayed a related but distinct mechanism. Its fault orientation was approximately perpendicular to that of the magnitude 4.7 event, while the solution showed a strong strike-slip component oriented northwest to southeast. Researchers noted similarities with a magnitude 4.4 earthquake that struck the same general area in May 2025. That comparison suggests that the July swarm did not necessarily activate an entirely new fault system. Instead, it appears to have reactivated structures that had already participated in the recent seismic unrest. Several additional earthquakes, larger than magnitude 3, reinforced that impression. 2 occurred south of the magnitude 4.7 hypocenter. Another appeared close to the zone associated with the magnitude 3.8 earthquake, and another occurred near the Aeronautical Academy in Pozzuoli. That final event was exceptionally shallow, at only about 200 meters, or roughly 656 feet. Its seismic waveform contained unusually strong low-frequency oscillations and prolonged resonance. Researchers say these characteristics are likely influenced by the extremely shallow source, nearby seismic stations, and the complex properties of the rocks and hydrothermal fluids beneath the area. Hydrothermal fluids are particularly important when interpreting Campi Flegrei. The caldera contains an extensive hydrothermal system where heated water and gases circulate through fractures beneath the surface. These fluids can alter rock properties, change pore pressures, and influence the way seismic waves travel. INGV notes that the unusual waveform characteristics observed during some of the very shallow earthquakes are linked to the presence of hydrothermal fluids and the strong heterogeneity of the shallow crust. This does not mean that every earthquake is caused directly by magma. It means the volcanic plumbing and hydrothermal environment can strongly influence how stress is transmitted and how earthquakes are generated. The broader deformation data add another layer. INGV's latest monthly assessment reports that uplift is continuing, although its rate has progressively decreased in recent months. From the middle of December 2025, the average monthly uplift rate was approximately 15 plus or minus 3 millimeters per month. Since early February 2026, that average has declined to approximately 10 plus or minus 3 millimeters per month. At the Wright GNSS station, total uplift since November 2005 reached approximately 167.5 centimeters, or about 5 feet 6 inches, including approximately 30 centimeters or 11.8 inches since January 2025. That slowdown is significant, but it should not be mistaken for a return to normal conditions. Campi Flegrei remains at yellow alert, which INGV describes as a state of medium disequilibrium with monitoring parameters above baseline values. The continued uplift means the ground is still undergoing deformation, even though the rate has changed. At the same time, the seismic system remains active, and the July earthquake demonstrated that stress accumulated within the shallow crust can be released through powerful events. A slowing deformation rate therefore does not automatically translate into a rapidly calming volcano. The system has to be evaluated through multiple independent measurements. Those measurements include seismicity, ground deformation, gas chemistry, and temperature. INGV reports that geochemical parameters continue to confirm longer-term heating and pressurization trends in the hydrothermal system. At the Solfatara target area, measured ground carbon dioxide output was estimated at approximately 950 tons per day, or about 1,046 US tons per day. Although this represented one of the lower values recorded in recent months, it remains elevated and comparable with emissions measured from persistently degassing active volcanoes. The important point is that no single parameter determines volcanic danger. Scientists examine the combined direction of all available signals. The July earthquake therefore becomes more meaningful when viewed as one component of a multi-parametric system. Seismic activity tells researchers where the crust is breaking. GNSS stations reveal whether the surface is moving. Tilt meters can detect changes in the angle of the ground, while dilatometers monitor changes in strain. Gas measurements provide clues about the hydrothermal and magmatic system, and thermal observations can reveal changes at the surface. Each measurement has limitations, but together they can show whether different parts of the volcanic system are changing in a coordinated way. That is why the new earthquake data are valuable even without indicating an imminent eruption. The artificial intelligence analysis may ultimately prove just as important as the deformation measurements. Researchers from INGV, Stanford University, and the University of Naples Federico II developed algorithms trained on the earthquake catalog produced by human analysts. Applied retrospectively to data from 2022 through 2025, the system identified more than 50,000 earthquakes within Campi Flegrei. That is a remarkable expansion in the number of tiny events available for study. Small earthquakes may appear insignificant individually, but collectively they can illuminate the architecture of active faults and reveal patterns that conventional catalogues cannot resolve. When the same approach was applied to the July 31st through August 2nd sequence, the difference became immediately apparent. Routine analysis had identified roughly 450 earthquakes, while the artificial intelligence system located more than 1,000. That does not mean that hundreds of earthquakes were somehow hidden from scientists in real time. Rather, the algorithm was able to revisit recorded waveforms and recognize very small signals that are difficult to distinguish visually. The result is a much higher resolution seismic photograph of the swarm. Researchers can now examine not only the strongest earthquakes but also the smaller events that outline the activated structures. That capability could become increasingly important during future episodes. Campi Flegrei is a place where subtle changes may matter, but subtle does not necessarily mean predictive. A cluster of tiny earthquakes does not automatically mean magma is rising toward the surface, just as a magnitude 4 earthquake does not automatically signal an eruption. Scientists instead look for changes in location. depth, earthquake mechanisms, deformation rates, gas emissions, and other parameters occurring together. The artificial intelligence system is still being tested in the monitoring room, with the goal of determining whether it can eventually assist analysts in real or near real time. The spatial distribution of the July swarm provides another important clue. INGV reports that a large portion of the central caldera became active, but the earthquakes occurred mainly along structures already involved in the current unrest. The principal fault structures beneath the submerged sector of the caldera were not activated during this sequence. That is a crucial observation, because it places limits on what can reasonably be inferred from the earthquake pattern. The swarm did not demonstrate that every major fault beneath the entire caldera suddenly became active. Instead, it concentrated within the already known central zone of ongoing deformation and seismicity. This is where the idea of a major change needs to be handled carefully. There is clearly new information, but the change is not necessarily evidence of a new eruption pathway. The strongest new development is the resolution with which scientists can now see the seismic sequence and its associated deformation signals. The data show a shallow, migrating swarm activating established structures, while GNSS, tilt, and strain instruments recorded discontinuities associated with the strongest earthquakes. That is a genuine change in the measured state of the system, but it is different from claiming that the volcano has entered a pre-eruptive stage. The distinction matters because Campi Flegrei has a history that can easily encourage dramatic conclusions. The area has produced enormous eruptions in the geological past, including events capable of reshaping the landscape across large portions of southern Italy. But geological potential and short-term eruption probability are not the same thing. A volcano can possess enormous eruptive capability while remaining in a period of unrest rather than eruption. Scientists therefore avoid treating individual earthquakes as countdown clocks. Instead, they ask whether the entire system is moving toward conditions that indicate magma ascent, increasing pressure, or destabilization of the volcanic plumbing system. There is also another reason the July earthquake deserves attention. It represents the largest energy event recorded at Campi Flegrei by the modern instrumental network. INGV says the event brought the total number of earthquakes with duration magnitude 4 or greater since the beginning of the current unrest in 2005 to 11. These events have become concentrated in the more recent portion of the ongoing bradyseismic crisis, reflecting an increase in released seismic energy over the past 3 years. That trend does not provide a precise eruption date, but it does demonstrate that the current unrest is producing increasingly significant earthquakes. For people living in Pozzuoli and the wider Naples metropolitan area, the distinction between magnitude and impact is particularly important. The July 31st earthquake was shallow and close to populated areas, producing strong shaking and damage. INGV's urban accelerometer network recorded the event across the area, allowing researchers to reconstruct the distribution of ground motion and estimate potential effects on buildings and infrastructure. The Institute is using this dense monitoring network not only to study the volcano, but also to understand how repeated earthquakes affect structures over time. This represents a practical application of volcanological monitoring directly connected to public safety. The event also exposed why repeated moderate earthquakes can become a serious engineering problem even without a volcanic eruption. Structures do not experience only one earthquake in isolation. Repeated shaking can contribute to cumulative damage, particularly where buildings were not designed for modern seismic standards or where earlier earthquakes have already weakened components. INGV's urban monitoring project is intended to improve estimates of vulnerability and the probability of damage during earthquakes. By tracking the response of buildings as well as the movement of the ground, scientists can potentially identify deterioration earlier and improve assessments of which structures are most exposed. Meanwhile, the wider caldera continues to rise. At the right station, approximately 167.5 centimeters or 5 feet 6 inches of uplift has accumulated since November 2005. That figure is not a sudden jump caused by the July earthquake. It is the cumulative result of years of bradyseismic deformation. The distinction is essential because a long-term uplift trend and a short-lived seismic displacement are different phenomena. One reflects the broader evolution of the volcanic system. The other reflects an abrupt response to fault movement. Understanding their relationship is one of the central challenges of monitoring Campi Flegrei. Scientists are therefore watching not simply whether the land rises, but whether the rate changes, accelerates, or becomes spatially concentrated. A volcano can deform for many years without erupting, and Campi Flegrei has demonstrated precisely that kind of prolonged unrest. What matters is whether deformation becomes accompanied by other independent signals pointing toward a significant change in the subsurface system. Those could include accelerating seismicity, changing earthquake depths, new seismic mechanisms, unusual gas trends, thermal changes, or deformation patterns inconsistent with previous episodes. None of these signals alone provides a reliable eruption timetable, which is why the monitoring strategy is deliberately multi-parametric.